Okay, so very good afternoon. Okay, so we have started the first session first session after the launch. Okay, this is third session of our ongoing workshop. So, so I'm requesting to the participant kindly mute yourself. Okay, so okay, this session is basically discussed with that energy management strategies. Okay, for our microgrid system with the hybrid storage. Okay, so I'm requesting the participant please mute yourself. The session will be taken by Ms. Pranati Rani Purohit. Okay, madam, you can start your session.
Thank you, sir. Shall I start, sir?
Yes, ma'am, you please start.
Okay, sir. Thank you. Good afternoon, everybody. The present topic of the session is energy management strategies for renewable energy systems integrated with hybrid energy storage. Now the contents are, these are my contents besides introduction. It contains role of the energy management system, then a present DC microgrid system, then control architecture, then simulation results, then I have also added the robustness studies, then conclusion. Then coming to the introduction, all of us know what is a microgrid is. Microgrids are localized networks that contains our renewable energy resources as well as the hybrid energy storages. Now, what is meant by hybrid renewable energy storages? These are the RPV, wind, or any other DC that we can generate. DC, basically, this is a DC microgrid we have considered. So, renewable energy systems, I have considered here with PV and wind. Now, hybrid energy storages include our batteries and supercapacitors. Now, we need a EMS energy management strategy for this one. But before going to that one, as we know, microgrids are classified as AC and DC based systems. Now, advantages of the DC microgrid. See, there are different advantages of AC systems and DC systems. All of us know it. Now, let us not go into it that one. Uh, these are the advantages of the DC microgrids because no frequency is involved and it is easy to integrate our energy storage systems. Synchronization is not required and absence of reactive power and frequency control. Now, going to the role of, now the topic is why the energy management system is required. Now, we know that when we have renewable energy systems and energy storage systems, both are in hybrid mode, we need a coordinated operation between them to meet the load demand and their intermittent nature. What is their intermittent nature? Because their output varies with the environmental conditions. We do not know the environmental conditions. Accordingly, the renewable energy output varies. Therefore, we are dependent on the energy storage system. Now, and for energy storage system, battery would have been sufficient for long power deficiencies. But when it comes to sudden power deficiencies or to take the transient part, we are dependent on the supercapacitors. So we have considered here renewable energy system along with the hybrid energy system, which contains the battery as well as the supercapacitor. Now, when we work with the renewable energy system, hybrid energy storage at a time, besides the coordination between them, we need the DC bus voltage to be maintained constant for a particular system. So, for that DC bus voltage system, again reflects the balance between the supply and demand, supply from the renewable energy end, and demand from the consumer side, which when deviates, it includes our instability in the system. Now, to maintain the DC bus voltage is our primary importance. So, the microgrid must charge and discharge the energy storages properly in spite of the environmental conditions or the load changes. That is why our that is why we need a proper energy management system for this renewable energy systems integrated with hybrid energy storage systems. Then coming to the system configuration, this is our system configuration. Now this is a wind system and this is a PMSG based. The system configuration can be chopped into these three sections. One is our wind power generation, which contains a PMSG, permanent magnet synchronous generator, and a rectifier. Now this is our buck converter. As we are comfortable with the buck converter, because I need a voltage of 48 volt here, depending on my system. This is my DC bus voltage. So I am generating a little bit higher voltage here. Therefore, I have used a buck converter here. Then this is a PV panel and I have used a boost converter here to maintain the DC bus voltage at 48 volt. Then a battery and a supercapacitor as the hybrid energy storage. Both are connected through separate buck boost converters which are bidirectional in nature. Then this renewable energy sources of PV, wind, and the hybrid energy storage of battery and supercapacitor are connected to the DC bus, which is further connected to the load. All these are controlled by means of this power management scheme, or we call it as energy management scheme. Now for the system configuration, I have considered the design parameters as for the photovoltaic array 500 watt and for the wind system 700 watts. For the battery 24 volt 36 ampere hour, I have connected two 12 volt batteries for this one and a supercapacitor of 32 volt and 58 farad. Now bidirectional converter, I have used LC values. It depends on your particular system. LC values you can find out according to your system. Then the control architecture of the power management. Now for the power management scheme or the energy management scheme, we have a reference voltage which I have used here as the 48 volt. It depends on your reference voltage what you can choose. Now which is compared with the DC bus voltage. Now DC bus voltage is this DC bus voltage which I have, but I need it around at 48 volt exactly. So what is my present DC bus voltage value? I need to keep it at 48 volt. For that, the present DC bus voltage at any moment of time should be compared with the reference value. I have considered reference as 48 volt. Now, when these two values of voltage are compared, that is passed through a voltage controller. This TFV controller is transfer function of the voltage controller. Any you can consider any controller here, say PI controller, or or you can connect here a fuzzy controller, sliding mole controller, or a robust controller, or any of the kind of the controller you are comfortable with. You can connect a controller depending on its performance. Then it is a low pass filter we have connected because this voltage controller generates our net current. Now the net current is divided into two parts. One part goes to the battery and another one goes to the supercapacitor. Now which goes to the battery is passed through the low pass filter and with the high frequency component passes through the supercapacitor and the low frequency component passes through the battery. Now, so that is why it is our average component and this high frequency component is or the transient component is passed through the supercapacitor. Now, This all we have, this VB by VSC is one small factor which we have considered, and this is battery current error which we have considered to enhance the output, or so as to keep the voltage exactly at 48 volt after experimental studies. And this A value also is to be found out numerically, and B values, these all are either to be found out through numerically or used through the optimization technique. This two needs to be found out, which goes to the energy management strategy, then which goes to the PV controller, wind turbine, or as we are considering, or we are concentrated on this battery and the supercapacitor, the low frequency component goes to the battery reference current, which is again compared with the battery current. Now, battery current, are you getting me? This is our voltage controller, low pass filter, low frequency component passes through the battery, high frequency part passes through the supercapacitor. Then it generates the battery reference current and supercapacitor reference current accordingly when it is passed through the energy management strategy. Then which is compared with the battery current and the supercapacitor current. Now, what are battery current and supercapacitor current? This battery current and supercapacitor. I have written it capital B, but it can be small b. This battery current coming out of the battery. This is supercapacitor current coming out of the batteries. Now, this reference current of battery and the supercapacitor are compared with the battery current and the supercapacitor current, which is again passed through a volt current controller, as this current to difference of the two currents passes through the current controller. Now, this controller can be same as the voltage controller, or it can be different also. This can be your traditional PI or 2D or 3D or PI or whatever controllers you are using, or robust controller. Then this is our, it passes through the pulse width modulated signal, and it SB1, SB2, SC1, SC2 are the four switches. Then the control architecture of the PMS. Basically, in the control architecture of the power management strategy or energy management strategy, we need to find out what is the high frequency component and what is the low frequency component. Now, the PMS leverages a hierarchical control structure that distinguishes between power demands average component and average component, low frequency component, and the transient component. That is the job of this energy management strategy. Now, the steady state component is the low frequency component, which means slowly varying part of the power mismatch, and now the sudden component or the dynamic component is the high frequency component, which represents the transients in the load or generation. Now, the power, if the power generated by the renewable energy source is at any point of time is P REST, this is P renewable energy sources at any instant of time. Now, as we have used only PV and a wind system at any moment of time, the renewable energy power is equal to the summation of the PV power plus the wind power, which requires to regulate the DC bus voltage is P net. Now, net power is the renewable energy source power minus any load power minus the losses occurring. So, the net power is here are battery power and the supercapacitor power. P net, PV, wind, this character, PB, PSC, this characterize the PV wind systems. Then further, the net power is again divided into the battery power and the supercapacitor power. So these two are differentiated by this bar and the cap power of the P net. This is low frequency component power. This is high frequency component power, which is equal to DC bus voltage multiplied by net current. Now, net current is once again what? Coming from the battery and coming from the supercapacitor. This is the average current coming from the battery. This is the transient part coming from the supercapacitor. How to find out this average component? which is net power by DC bus voltage. And transient power is net power divided by DC bus voltage at that particular instant of time. Now, renewable energy current is, as we know, PV and the wind turbine current. INET is the net current at the DC bus. Here we have mentioned everything. PNET is the average active power component. PNET is the sudden variations in the RES or load power. This is our transient power. PNET bar is our average or active component. Now the net current at the DC bus is obtained. Net current now as let us go back. Net current is this one. Net current is obtained when the reference value of the voltage is compared with the DC bus voltage and passed through a voltage controller. It generates our net current. Net current is the summation of average current and transient current. This is our average current and this is our transient current, that is battery and the supercapacitor. So net current is summation of the average component of current plus the transient component of current, which is KPI dot VI error. KPI is the transfer function of the PI controller, or whatever controller you are using here, you can consider that transfer function multiplied by V error. Error is the difference between the reference value of the DC bus voltage and the DC bus voltage. So VERR, we call it as the error value of the voltage. Now PKPI is the transfer function of the voltage controller. Now for the successful implementation of the energy management scheme, it depends on the specified currents at the DC bus, that is the average component of current and the transient component of current. Now we need to differentiate, or we need to segregate this low frequency component of current from the high frequency component of current provided by the batteries and the supercapacitor. The net current is traversed through a low pass filter, as we have seen there. This is our low pass filter, net current divided into average current and transient part. This is net current when passed to the low pass filter generates the average current, and then this low pass filter, the difference of this current and this current, that is the currents at both the ends of the low pass filter, is decided as the transient part. IB reference is the net current multiplied by transfer function of the low pass filter. Now, the low pass filter, you have to in the low pass filter, when you work with the simulations, you have to once again arrange the time constant there and the frequency. So I have considered in my present studies 0.125 as the low pass filter time constant. You can, for this also, you have to tune and find out the time constant for your system. Then this is your average component. It generates our average component. That is when the battery reference current or net current multiplied by the low pass filter transfer function, it generates the average component. Similarly, for the transient component, which is of the supercapacitor, that net current is multiplied with the 1 minus LPF. That is the current from the two ends of the low pass filter, and then which is added to the voltage error multiplied by any constant A and B. Here are two constants which are decided through any optimization techniques or trial and error, or it can be decided experimentally also when we use the experimental validations. So our supercapacitor current or transient current is the net current multiplied by 1 minus transfer function of the low pass filter plus any constant A multiplied by voltage error plus any constant B multiplied by the current error multiplied by the ratio of the battery voltage to the supercapacitor voltage. Now, this ratio is used to find out or to get the, it's like these all are a part of the research development where these ratios are uh, when the like energy management strategy takes into account the voltage, battery voltage and the supercapacitor voltage, it tries to accumulate the 48 voltage accurately. Then the battery and the supercapacitor current are computed. Battery current error is the battery current reference value minus IB. As we have, can we go back and see IB reference and IB? This is our reference current, what is being generated from the energy management, and our battery current. Similarly, this is our I is supercapacitor reference and the supercapacitor current. So this is battery error. This is equal to I battery reference minus I battery current. Similarly, ISC error is ISC reference minus supercapacitor current. Now to create the duty ratios for the battery and the supercapacitor, it has to be the error values. This is error value of current for the battery. This is error value of current for the supercapacitor. They need to be passed through different controllers, PI1 and PI2. If you are using different ratios of Kp and Ki for the battery and the supercapacitor, if you are using the same values, you need not write down 1, 2. That is, when 1, 2 is not written, means the same Kp, Ki values are used for the battery and the supercapacitor. Now, this process is to charge and the discharge properly action of the hybrid energy storage system. The energy management system is able to maintain the DC bus voltage properly and to maintain a proper power balance between the renewable energy and the load. So the function of the energy management strategy here is to decouple the dynamic and the steady state power of the power components, and it provides a faster transient support, improve DC bus voltage stability, and it can regulate the hybrid energy storage properly. Now coming to the simulation results and discussions. So these are the parameters consider. I have considered here two case studies. One is variation in the generation, that is solar irradiance variation and wind speed variation simultaneously. We can consider it separately also. Now the simulation configurations taken for the case study 1 are the time I have considered 0 to 14 seconds. That is each of 2-second durations within 2 seconds are a load power. Now, in the first case, this is our case 1 where the load is kept constant. Load power is kept constant at suppose 770 watt and DC bus voltage is 48 volt. Now the generation is varying, so PV power is varying. See, the PV power varies in each step. Initially, it is increasing and then it reaches its maximum value of 500 watt, then it starts decreasing. So this PV power depends on the solar irradiance. This is the value of the solar irradiance. Accordingly, the PV power changes. Similarly, this is the value of the wind speed. Accordingly, the wind power changes. Now the wind power has started increasing till 700 watt. 10 watt is negligible, around 710 watt. Then the wind power decreases and at this point the wind power is curtailed to see only the effect of solar energy. If no wind energy is produced, then how far the system sustains with the solar power system. Now, these are the results of the simulations. Power management, we will go to the simulations to find out, to see the results also. Now, this is power management between RES and the hybrid energy storage system. This one is PV power. See, in each second, 0 to 14 seconds we have considered. In each 2 seconds, the PV power is increasing. See, this purple line is the PV power. PV power reaches and its maximum value of 500 watt. Then it starts decreasing. Similarly, the wind power or wind speed also increase. The wind speed values are written, corresponding wind speed values are written here for the clarification. Now the wind speed changes accordingly slowly, reaches its maximum of 700 watt, then slowly it decreases, and at this point the wind power is curtailed. Now see, when this is a supercapacitor, it can be seen that it takes the high frequency component. At the instant when the load changes, say from 0 to 2 seconds, 0 to 2 seconds, the PV power is 100 watt. G represents the solar irradiance. PPB represents the PV power. Similarly, BW represents the wind speed. PWT represents the wind power. PB represents the battery power. And this is our supercapacitor power. Now, you see from 0 to 2 seconds, PV power is 100 watt and wind power is 300 watt. 320 watt. So they combinedly PV and wind combinedly is the renewable energy system power that is around, that is 420 watts. So you can see this load power is constant at any moment of time here. Now load power is 770 watt. Load power is 770 watt. So renewable energy power is 420 watt. Load power is 770 watt. So at this 0 to 2 seconds, the renewable energy power is not sufficient to maintain our load demand. That is why the rest of the power is given by the battery, or we can say the battery starts discharging. At this point, the battery discharges and provides the rest of the power 350 watt to complete our load demand. Similarly, from 2 to 4 seconds, you can see that PV power goes to 200 watt and the wind power is 475 watt. But our load power load power remains constant, whereas this generation is 475 watt plus 200 watt. The 770 watt minus the combination of this PV and wind power is given by this battery. You can see that if the controller works properly, whatever we have used, the gains we have set properly, then even for a small variation of the 95 watt also, PV battery power discharges and the curve is shown properly. Then from 4 to 6 seconds, we can see, now at this 4 to 6 seconds, we can see that PV power has once again increased to 350 watt and wind power has increased to 660 watt depending on the irradiance increase and the wind speed increase. Now, when PV power and wind power increases, but the load generation is constant, but the renewable energy generation is more than the load demand. So we can see that the extra power is taken by the battery, or we can say that at this point of time, the battery charges, which is given by the minus sign. 250 watt, that is 350 plus 660 minus 770 gives our, the net power is given by the battery as minus 240 watt. Similarly, at this point also, battery provides the power of minus 440 watt. And at this point, 6 to 8 we can see that it is at the maximum value of 500 watt PV power. It is at the, and wind power is at a value of 710 watt, because the irradiance here is 1000 watt per meter square and here it is 12 meter per second. Now, when these two are also more than the load power of 770 watt, the extra power is taken by the battery minus 440 watt. So in this part, we can say that the battery charges. But once again, when it reaches the 10 seconds, see at 10 second, what happens? The PV power suddenly decreases to 250 watt and wind speed decreases. Therefore, the wind power also decreases to 150 watt. So they combinedly are not capable of producing the sufficient power for the load demand. That is why the battery once again discharges for 370 watt to supply the extra load demand. Then at this point, 12 seconds, you see that the wind power is curtailed, means no wind power is zero here. So only the PV power, that also is less than the load demand, which is equal to 300 watt, which is not sufficient to produce the load demand of 770 watt. Therefore, the battery gives the 470 watt power, rest of the power. In this way, the energy management strategy or the power management strategy, which are either way represented in the literature, this is the power or energy management between the renewable energy system and the hybrid energy storage system. Now for the current management and DC bus voltage regulation, you see for the current management, we can see the different values of the current, of the load current, battery reference current, battery current, supercapacitor current. Now, one thing I forgot to tell you in this slide, see, besides this power management of renewable energy storage system and hybrid energy storage system, we need, when we will see about the only about the hybrid energy storage, that is the battery and the supercapacitor. Look at the supercapacitor power. Only when the load changes, sorry, here we have not considered the load change, we have considered the generation change. When the PV generation and the wind generation changes, at that instant, the instantaneous power is supplied by the supercapacitor. See, each instant of the change of the generation, see, the supercapacitor supplies the instantaneous component or the transient component, whereas the average component is provided by the battery. Now coming to the DC bus voltage regulations, see, this is the 50 volt regulation, and with our simulation, it goes to, it settles around very less than 50 volt, around 49 volt it settles, and this is our reference value, and this is the DC bus voltage value. DC bus voltage is exactly kept at the reference value of 48 volt. We can see from this one, and these are the changes are when the generation change. When the load increases, the voltage increases suddenly, but due to the controller action and the EMS coordination, it comes to 48 volts, settles within very less time. So within 0.1 second, it can be said that it has settled to, from 0 to 0.1 second, it has settled at 48 volt only. Then at the instant of second time generation change also, it is shown that 48 volt, it remains constant and it goes to 49, more than 49 volt, but less than 49.5. Here, when when the generation changes little bit more, see here, the generation change is less compared to this point. That is why the voltage change is also less here compared to this point. Because here the generation changes more, so the DC value also fluctuates little bit more than 49 volt. That is why I have considered these points where the fluctuation is more. And here the generation changes is less compared to this point. That is why the DC bus voltage variation is also very less. We have considered and we have shown that this is the maximum value of DC bus voltage change for sudden generation changes. Similarly, when the generation decreases, this point is when generation in this point is first initial point is when generation is given suddenly, and this is when generation changes suddenly, and when this is when generation increases suddenly, and this point is when generation decreases suddenly. This is our 48 volt. At this point, we can see that even the energy management strategy or the or the controller is able to maintain the voltage at 48 volt and very less deviation around 48.5 volt. As the generation is decreasing here, a decrease in the DC bus voltage is found here, which settles around 48 volt. Then we can see that battery voltage, and this is supercapacitor voltage. The change in the super battery voltage for the from 0 to 14 seconds for the change in the charging or the discharging process. Initially we have seen that the battery discharges for 2 is from 0 to 4 seconds, the battery discharges. So we can see here from 0 to 4 seconds, the battery discharges. Then this is our supercapacitor value. This is the state of charge of the battery for the discharging and for the charging values. And this is also very less variations from point values variations. We have, that is why 22 to 25 we have considered. This is SOC of the supercapacitor. It is clearly visible from the state of charge of the supercapacitor that it is constant and it responds for the transient part immediately at these portions. Then we have considered a case study, second case study for the fluctuating load demand. Case 1 was for the fluctuating generation, and this is for the fluctuating load demand. Then for the fluctuating load demand, 0 to 6 second is considered. That load power is uh, increasing and then decreasing. PV power is kept constant, solar irradiance is kept constant, wind power is kept constant, also the wind speed is constant. I mean to say that the renewable energy power is maintained constant. The PV power, wind power is maintained constant, and what varying here is the load power. So 0 to 6 second is considered to find out the simulation results. Then these are the fluctuating load demand. We can see that the load here is 768 watt here, then 1024 watt, then 1484 watt. And you see the PV generation I have kept constant, wind generation also I have kept constant from this 0 to 6 second. The wind PV power is taken here 500 watt, which is mentioned, and wind power is 710 watt. Then the load power, when it goes on increasing, see battery continuously means each point, see from 0 to 2 seconds, we can see that PV power is 500 watt and the wind power is 710 watt, which is more than the load demand. That is why the battery charges. At this point, battery is charging. Now, at this point also, we can see that 710 watt plus 500 watt. It is around 1200 watt, which is again more than the load demand. That is, the generation is more than the load demand. That is why the battery is also charging with minus 180 remaining, 186 watt. Now, at this point, we can see that when the load power suddenly increases, the 1200 watt of generation of renewable energy system is not sufficient to maintain the load demand. That is why the battery starts discharging. Battery is given as 274 watt plus value. And coming to this DC bus voltage variations, this is the reference value, this is the DC bus voltage. See, these three instants are shown. First one is initially when it is introduced, second is at this moment, third is at this moment, that is during the load change. Load, see here the 48 volt, this is our 48 volt. It settles within 0 to very less than 0.5 seconds or 0.05 seconds also. Now, when the our generation is less, see the voltage starts decreasing, but again reaches our 48 volt immediately. Similarly, at this point, it can be seen that it reaches our 48 volt immediately. Now, SOC of the battery, and this is SOC of the supercapacitor. Then robustness studies. Besides this power management strategy, the power management strategy or the controller, this should be validated always with the robustness studies. Now, if robustness studies, I have considered here the robustness studies with respect to the parameter variations. That is, if some change occurs in the parameters connected of inductor and the capacitor values or any of the parameter values, then the proposed energy management strategy or the controller combinedly in coordination should be able to sustain the DC bus voltage in spite of the deviations in the parameters. So, the robustness studies is a necessary part. Initial values of L and C are this one. Now, 33.3% is increased values of the inductor is considered. For the capacitor also 20% capacitor decreased values are considered, which gives the simulation results as with the robustness studies, without parameter variation and with power meter variation. See, DC bus voltage, the DC bus voltage, we can see that uh, this without parameter variation was coming in this one, and with parameter variations also, that is even with the inductor and the capacitor parameters vary in the simulation, very less effect it has on the DC bus voltage. So at a time, suddenly it comes to 48 volt. See, for the variation is from 0.005 second. Okay, this which is a very less time, and within that it settles at 48 volts. So we can say that the simulation or the proposed energy management strategy coordinated with the controller is able to sustain the DC bus voltage at the reference value. Then the load power of the load, we can this load power, why I have considered for the parameter variation is that when the parameter values changes, it affects the load power also. That is why this load power variation is seen. without parameter variations and with power variations. We can see that very small portion is shown, and for this 10 to the, even in the milliseconds range, here see here we should not be confused. 2 to 10 second written, it is in milliseconds. 10 to the power minus 3 is written. Time is in milliseconds. Within this milliseconds range, the energy management is able to sustain the DC bus voltage to 48-volt reference value. Now this is our PV power and the wind PV power and the wind power. Even the renewable energy power along with this load power is um, able can fluctuate with the parameter variations. But we can see that here with this proposed controller and energy management strategy applied properly, then the variation is very less. Here in the PV power, here in the wind power. See, wind power settles properly around 700 watts. This also, this is 0.02 seconds, and this is very, very less in milliseconds. It settles to 500 watts properly. Then the robustness studies is also considered with the battery power and the supercapacitor power. Now the battery power, this is without parameter variation, and which power variations they overlap with each other, which shows that it has negligible effect on the battery power as well as on the supercapacitor power. Now this is a repetition to say that the battery power is considered as the low frequency component, then supercapacitor takes the high frequency component part, for which the spikes are visible in the supercapacitor part at the instant of load change. See this two instant of load change at 1 to 3 seconds. Or if this we have run for 3 seconds to show the load changes. Now, before going to conclusions, we need to go to the sharing part of this simulations is there, where we have considered, where we have connected the battery and the supercapacitor parts, where we have considered the battery and the supercapacitors. The wind power system is considered, then the PV power is considered, and battery and the supercapacitor is considered. So we can see from this one that the, okay, let me again run the system for uh, let me take a few seconds to run the system, so we can see that the power management strategy works effectively in coordination with the suggested control strategy. Everything is working. Why this is not showing? It was coming actually. Why this is not showing? I do not understand. Let me run the system again.
Hello, good afternoon.
Ah,
Am I audible?
yes, you
See,
are audible.
actually, I have few questions. Meanwhile, can I ask?
Okay.
Like,
Sure.
okay, what optimization method have you used for this? Like in the control architecture of EMS, like you have mentioned
Huh.
that some optimization you will be using to get the
Hmm.
references. So
I
currently,
have used a simple particle swarm optimization technique, and the
okay,
rest genetic algorithm is also working fine, and many advanced techniques also have come. But I
like
have used the
PSO. And about the like controllers, what controllers have you used for different for converter controls of different like PV, wind, battery, supercapacitor, etc.
see, there are PI controllers are variety. Everybody is using or industry is using. And besides that, the various degree of freedom of the PI controllers are used. But we have tested the system with the robust controllers also and
Okay.
cascaded controllers also.
Robust controller like means what
Robust
control?
controllers is like H infinite controllers and many other controllers in combination with the PI controllers are also available as the robust controller, or we have tried fuzzy logic also. Fuzzy logic also is working fine. You need to write the or tune the parameters of the controller properly. Either you use the PI controller or use the any other robust controller or degree of freedom, whatever controller you are using. You need to arrange or find the parameters properly according to the values of your system in the simulation.
Like
Then it will work fine.
for PV, have you considered any detailed model or like average model like whatever available in uh, Atlanta?
We have considered only the average model for the PV because I have concentrated only on the simulation part.
Hello.
It's on hold. Hello.
Am I audible to you? Am I
Yes,
Yes,
audible?
ma'am.
madam. Yes, madam.
Yes, ma'am.
Okay. It was disconnected from my end actually. I was showing the result. Is it visible now?
Yes, ma'am.
Yes.
Okay.
What is the DC bus voltage in your case? Like,
I have taken 48 volt as the DC bus voltage reference value. You can take any value. See, I have considered a low voltage microgrid. So I have considered 48 volt because I have considered PV power and wind power less than 1000 watts. So I have considered 48 volts.
so PV
Some
for PV
researchers
power.
also consider, okay, some researchers also consider 50 volts, 70 volt. You can go ahead with it also.
Okay, for PV power extraction, like, have you considered any techniques like MPPT and all, like, or like generally, like you considered it as a control current source or like that?
For PV, I have shown na, I have used boost converter, and for the boost converter MPPT, if you do not use a converter for that one, even for the PV and the wind, it will not give you the MPPT values properly. For the maximum power points, it will not work properly. That is, so you have to use MPPT values, MPPT converters for that one.
Okay, madam, 48 volts is fine because 12, 24, 48 multiples, that's perfect.
Yes, yes,
Then the current wise, usually if the realistic models, like suppose if you want to charge an EV, at least 2
okay,
kilowatt in the wind generators, 2 kilowatt is also very practical in the market.
yes,
So the current wise, instead of 500 watts or 1 kilowatt, 2 kilowatt model, that gives that meets the realistic requirement in the market in the commercial.
okay,
Then a second thing, one thing I'm observing is your renewable energies. Okay, the power is coming, and then when you are
yes,
storing, we can, I think, we can consider a centralized battery system, storage system, and then we are
yes,
decoupling and then coupling. Decoupling from what? From the load. So it won't see the load will not see the variations in the renewable energies. And at the same time, the load variations will not be seen on the battery storage system. So I think in the maybe you may think in better way. So in decoupling system, the centrally the bus is there, and the bus will store the energy, and then this
mm,
energy is given to the DC coupled or DC-DC, and then to the actual load where it is running. So the load always is the constant voltage there, and the battery which is driving the load will not see the variations in the renewable energies because it's stored in the centralized system. So like a
okay,
DC-DC and DC coupling. Because actually we are working on the system exactly what the system you said, we are 48 volt DC we are generating, and wind and so solar, any compensation is required, we are managing. And then what exactly you said, the battery and the solar, like a super capacitor, super capacitor. Okay, but that techniques we are using. But on the load side, this battery once it is charged, then will the DC-DC charging will be there, and that
you are not audible now. You are not audible now.
oh, maybe
Huh.
the down. Now can you hear me, man?
Yes,
Uh, so the DC-DC coupling and the two-tier system in charging is one stroke, and then the load, the battery which is driving the load, that's different. So certain, we'll get some clarity in that, because it will not, the load will not see the variations in the renewable energies, and at the same time, the battery will not see, the central stored system will not see the variations in the complex loads. Will it be okay? Can we try that kind of systems there in your NIT Rourkela?
Yes,
Means,
that is once again, I think we need to consider that the demand side management also.
okay, yeah, yeah.
We are working here as the load side management. If we can
Mhm.
coordinate the demand side management as well, then we can work both of them coordinately.
Okay, okay, perfect.
Okay. Now coming to this energy management, see the when are extending. This is my load power. Each is written properly. Now this is our PV power. This is my wind power, as we had seen in the simulation slides. Exactly, it is getting PV power, wind power. This is load power is maintained constant for the case one. See, there are small spikes in the load change when the generation changes. See here, very small spikes in the load demand. Means the system is properly working. Now, PV and wind power, as the load demand is 770 watt is constant, as we had considered from 0 to 4 second, it is battery is discharging and this is charging, again it is discharging. Same is shown is the power management also. Then this is our current management. See, current management is, this is our super capacitor. This is our battery values, charging, discharging. Now here we can see that this is our super capacitor in the energy management. This is our super capacitor power. See the spikes are coming, means the super capacitor is taking up the transient part. Here they are taking up the transient parts. Then the DC bus voltage, see, it can be seen that the DC bus voltage is maintained constant exactly at the 48 volt in spite of this generation small variations. Then
Yeah.
we can see that, yes, sir.
So presently
Sir,
for the
is it?
same DC bus, the renewable energy is connected and the load is also connected, right?
I have connected same renewable energy system. Load is changing, and we can have simultaneously generation and load change also. Okay. Till then, the controller works fine. Now the battery current reference. See here we can see that battery reference and this is coordinate working. Battery reference current and the battery current. We had shown in the PPT. This is battery reference current and battery current. See, both overlap properly and exactly. Reference current and the battery current, which we had shown here in the diagram around. In the battery current and its reference current. When there is zero error between the reference value of the current and the battery current, then only it will have the 48 volt. So we can see that from the simulation, they exactly match. Reference current matches with the battery current. So the DC bus voltage is maintained constant at 48 volt at any instant of time.
Okay, suppose if it
Then this is
doesn't match, what happens? The load disconnected, load gets
not
disconnected.
like those kind of fluctuations will come in the DC bus voltage. It will not be maintained at 48 volt, but again, it depends on the voltage controller. So power management will not be proper at all. See, from the power management, we are seeing that when the generation is not able to maintain the load demand, then the battery is giving. So at that time, this power management will not be proper. Very a different value of battery will come. See, as we have seen from these values, see here also you can see it from this value. If I present it, see, this is 0, this is 200. So PV power is 100 watt here.
Yeah,
Wind
that
power
means,
is see around 320. Yes, the
yeah, that,
rest power is given by battery. If the curves do not match with each other, then the battery will not discharge or charge properly. It will
yeah,
not
that,
give the accurate value required for the load maintenance.
then load gets disconnected, or you have a separate battery system which takes the bus.
No, we do not have, no, we have already tuned the controller which works fine, and the battery is able to provide the exact value for the charging or discharging. After tuning, this is already done. So battery current that we can see from this battery current matches with this reference values. So why to disconnect the load?
Okay.
According to the load demand, the controller is working fine. The energy management is properly working because it matches with the reference. And you can see from this power management strategy that supercapacitor power is 0 and it gives the transient parts only. You can see at the time of the generation change, it gives only the transient part, instantaneous part. Rest power is given by the battery only.
Okay.
Then this is given from the battery value and the supercapacitor value. And this also we can extend and see very less variation. This is 0.1 second, even very 0.05 second, less than 0.05 second also battery. Sorry, DC bus voltage settles at 48 volt.
Yeah, ma'am, sorry to interrupt. I believe you
Huh.
are presenting the simulation part, but only the slide is visible to us, not the simulation. Since I may be wrong, but I
Same,
believe
whatever,
no, the
no,
simulation window.
whatever we have done,
No, ma'am. Actually, I think you are
simulation
explaining
window
the
is not
simulation.
visible.
No. Since from the beginning it is not visible. Only that
The
slide.
PPT is visible.
Yes. Only that PPT is visible to us. Maybe I'm wrong, but yeah.
Means this window of power management is not visible to you.
No, only the slide is visible. Control architecture of PMS is visible. What about others? I don't know. Yeah.
I don't know. I think this is visible. Okay, let me confirm then. Please, others, please confirm. Is the power management windows change visible to you?
Yeah,
I
the
have been
slide is
continuously. No, ma'am.
Madam, only slide is
For me,
visible.
also
Yeah,
control
ma'am.
architecture of PMS only, ma'am.
Yeah. From the very beginning, when
Oh,
you
is
no,
slide
till
only
from the
visible,
beginning,
ma'am.
it is not visible, ma'am. Only the slide
Oh,
is
sorry.
visible. So yeah, thank you. Can you please?
Madam,
You
you
should
please
have.
share. Pranati madam, you please share the
Yes.
entire screen. Okay. So whatever you will do, so it will be visible for all of our side. Okay, ma'am.
Sir.
Share the
Entire
entire
screen
screen.
only.
Yes.
Okay, sir. Okay, sir. ज़्यादा विकास का आशा
Hey.
Now is it visible?
Yes, yes. Yeah.
I think, sorry for the interruption. You could have told me. I didn't know that it's not visible.
Yeah,
I
it's visible.
told
It's
it
okay.
continuously. Okay. This is the energy management. I was showing this is the energy management. And same as we had seen in the screen, PV power, wind power. And when this PV power and wind power is changing, whereas the load power is maintained constant, we can see that battery is discharging till 0 to 4 seconds. From 4 to this much time, battery is charging. Once again, it discharges when the wind power is curtailed here. See, the wind power is curtailed here. Therefore, the battery is able to supply. And when we see this part of the uh, DC bus voltage value.
In the last, ma'am, in the last figure, like why super capacitor power is coming to the baseline? Okay, why it is happening?
Because it is only for the instantaneous power. Supercapacitors have the property that they will give the instantaneous power supply. If it is required, the battery is not able to produce, then it will supply the instantaneous power. That's all. It is not for the long term. That's what we are using hybrid energy storage systems along with the battery, because it will give us only the transient part at the time of load change or generation part change. These are the spikes here, which say
Yeah.
that a transient part is given by the supercapacitor immediately, and the low frequency part is given by the battery itself. That
Yeah,
is the
we
property
call
of
it
the battery at the, yes, sir.
yeah, we call it in rush current. Rush current means
Yes,
switch on
yes.
type of rush. So
Those
yeah,
are
rush
given
in
by the
rush current.
supercapacitor. Yes.
Yeah.
Only spikes confirm that they give the transient part.
Yeah.
Why it is in the negative side, like below 0?
That depends like switch on, switch off type. Suppose it's already in on side, then the switch off that gives the reverse side. See, it's like an capacitor differentiation. You take a pulse, differentiate. Rising pulse gives the positive, falling pulse gives you negative.
Okay.
Is it visible now, sir?
Yeah, visible.
Okay, sir. Okay, thank you. Now the battery current and the reference current exactly match with each other. We can see from this one, battery reference current and the battery current. This is reference current is given in blue, red is our battery current. They exactly match with each other, which says that the energy management is properly working in coordination with the control strategy. Then this is the DC bus voltage value. It is maintained constant. Each point we can see that the spikes for a very small time of 0.0 less than 0.02 second even. The DC bus voltage is maintained at 48 volt. Similarly, what else is this is this is our irradiance value. This is irradiance is changing, and we can see that the wind speed is also changing here. See, the wind speed is changing. So these are this robustness studies, and with this one, we am I audible to everyone?
Yes, ma'am.
Okay. So with this one, so the system MATLAB or Simulink model is used with the varying load and generation conditions. Now here we have significantly increased the load up to 92%, 92.7% to evaluate that even with this much increase of load, the DC bus voltage is
Ma'am,
maintained
you have
constant.
screen sharing issue. Means we can't see your the MATLAB screen. We seeing your the Google Microsoft Teams screen.
Okay, okay. Actually, it was unable to switch between both Microsoft and the MATLAB windows. Okay, then is it visible now? No, ma'am.
No, ma'am.
Not it.
Okay, okay. Okay, then.
Madam, are you sharing the entire screen or only selected screen? Entire window or the selected screen?
Now is it visible? No, I did it
Yes, ma'am. Now
entirely.
visible.
Now visible, but once again, MATLAB needs to be restarted actually. It says that index exists. Okay, whatever I had shown you in the MATLAB SOC battery is showing. Whatever we have shown in the simulation presented in the slides, the same thing is working in the MATLAB also. SOC of the battery, then SOC of the supercapacitor, SOC of the supercapacitor, and this one is irradiance value. This is our irradiance value changing, and this is our wind speed. See, the wind speed is changing. This is our wind speed, and this is our DC bus voltage. Even with any of the changes, you can see that the DC bus voltage is maintained constantly at 48 volts. So you can see here. So that is why we have taken it at a time, just to maintain that, just to show that it is maintained at 48 volt exactly. This is irradiance, this is wind speed, and this is DC bus voltage. That's all. Now, any other questions for this one? Other, I'll go to concluding part. We have increased the load up to 92%. Even that, with that also, the proposed energy management strategy works fine to keep the DC bus voltage at the 48 volt. And the variations is within the allowable range of plus or minus 5% IEEE range. Now you can use for the any low cost controllers or low rural microgrids, this one. And these are my references. Now, any questions for that? Any other questions?
Have you got any publication for this work?
I have communicated. Conference papers I have published and communicated the journal papers. But those are in the communication stage. If not any other questions from anybody, then thank you all. Thank you, everyone. I'm only the anchor of this program, so I should thank everyone for attending this program. Now, the next session will start at 5 p.m.
Yeah, hi.
As you all know.
Yeah,
Yes.
good afternoon, madam. So,
Good afternoon.
Yeah, so I don't know. Maybe this is out of context of this question may be out of this thing, but still, I would like to know. Let's say you decided the size of PV supercapacitor BSS for a particular means this is a constant load.
Ah,
Energy management involves a kind of load variations, generation as we are integrating more renewable to the grid nowadays. In
yes,
a low inertia grid, suppose if we are trying to stabilize the grid, particularly
yes.
the DC link voltage and all. So how we approach different size, basically VSS, PV, supercapacitor, and based on the maybe constant or variable load. So can you please just link this work with that? Is it possible to size
I,
the size, not only size and size, both things for a proper particular load, maybe this seven this load condition also. Have you considered that part
yes,
for this energy
yes,
management?
yes, yes. Yeah,
Yeah, thank you.
see, for anything, if we are designing this, we are going to run into a hardware platform also. So for anything, we need to first size the PV and the wind system or battery or supercapacitor. We need to find out their sizes actually. So depending on the bus voltage range. So yes, we are considering a low voltage DC microgrid. So we have considered the 48 volt, and for that one, I thought of considering around 1 to 1.5 kilowatt. That is why I have considered 500 watt PV or around 500 to 700 watt. Some people consider even 500 watt low voltage wind also. I have considered 700 watt. So combinedly, they give us 1 to 1.5 kilowatt. Within that range, we have to design the buck converter and the boost converter parameters actually to get the 48 volt. Is your question like that only, na?
Yeah, correct. Yeah, but this is a
Yes.
islanded mode of operation. Still, if we will
Huh.
consider, let's say, grid connected and
Yes.
the variable price and all these things. So how to size all the different component of the grid? That is
See,
basically my
price
question.
is
Yeah.
economy. Price is economy. You need to consider that economic conditions once again. You need to go to power system and find out the Lagrange's multiplier and find out the minimum cost function for that one. Those all are a different part. This part I have considered the DC bus voltage maintenance without considering the economic part. Okay. So even if you are considering the grid also, you have to find out the components, their ratings. We bother about the ratings. We have not gone to economy part. Then economy part, you have to find out the Lagrange's multiplier, minimum cost function, those you have to do. So that is
Like,
different.
what's the
Only here,
goal of
yes.
what is the goal here, like for this energy management strategy, like you are using?
Goal here is to use it in a low voltage DC microgrid in the islanded mode wherever the grid is not present. Or we can integrate it into the grid also, no problem. But our aim is to work in the hardware. This I have done in the hardware in the loop also. We will show it in the next workshop, maybe day after tomorrow it is there, and we are about to integrate it into the hardware part also. So we need to find out the ratings of each one properly.
Okay, ma'am.
See,
Like,
if we are,
what's the type of DC converter you are using for both EV and wind?
for the PV, I have used boost converter, and for wind, I have used buck converter.
Okay, like type of converter, if you can could kindly mention.
Type of converter means
Like there are
I think it's
several
simulation.
types.
So you may be expecting some hardware component. It's in simulation, right?
Okay.
yes. Hmm. Depending on the output of the PV, you need to design output voltage actually, output voltage of the PV and what is your DC bus voltage. Keeping in mind these two voltages, you need to find out the boost converter rating, LC values. Then it will work fine. Similarly, for the wind also, what is the output voltage of the wind and what is the requirement of the DC bus voltage. If you consider these two voltage values and find out the LC parameters of the buck converter for the wind system, the system will work fine.
Yeah, thank you. Thank you. Actually, yeah, so that is that was my question. Basically, your battery size should be optimized with PV and wind, I think so. So that was my question, how to size that part, because the load is constant. When in
Okay.
Indian context, let's say irradiance is increasing and decreasing, wind speed is night time increasing, how to charge the BSS and optimally how to coordinately control that constant load. Yeah, that the sizing part I asked. Yeah, thank you for your good explanation. Thank you.
Thank you very much, sir. So, the participants, thank you all for attending or for giving time to listen to me or a patient's hearing. Now the next session will start at 5 p.m.
Thank you,
all.
ma'am, for delivering very nice presentations with your proper simulations. I think all the participants can also enrich their knowledge about the EMS and their implementations. Okay, so thank you. And our next session will be a laboratory session that we are trying to do some videography. Okay, so that will be started from 5 p.m. So in the meantime, if we can take some small break. Okay, thank you.
Thank you.